Having looked at the different options to solve the problem of merging two sorted lists, let's now focus on the two-pointer algorithm for this problem. The way we are going to go about this is that we are going to set up a pointer for each list. Now this is different from the pair sum problem where we had pointers pointing on the same list, but here we are going to point them on different lists. In fact, both the pointers are going to start at zeroth index of the list. Again, this is different, so there's no left or right here. Both point at the zeroth index, so I just call them pointer P1 and P2. So P1 goes to, for example, A0 and P2 goes to B0, where A and B are my two lists. Now I ask myself a question: if A P1 is less than or equal to B P2, well, I need to append A P1 to C and I will increment P1. If on the other hand AP1 is more than BP2, well, I will append BP2 to C and I'll increment P2. So the point is, we see whichever is the smaller of the two, we append that to the list, and that is the pointer we increment. Right? So that's the idea, and we keep doing this till either of the pointer becomes more than the list that more than the length of the list at which they are pointing. This is very interesting. Both the pointers must be pointing within the list. The moment either of them becomes more than the length of the list, the algorithm stops. Now this gets quite interesting in case of unequal length. We'll see this later. Now the interesting bit is that since the lists are sorted, basically the remaining items from the other list can be added directly. We'll see this in action. Quite interesting. So let's take an illustration here. Let's say I have two lists. Now I've taken lists of equal length to start with. So 1, 2, 8, 12, 17, 3, 4, 9, 12, 13. So I start with both pointers being where they are. Clearly 1 is smaller, so I add 1 to the list. I increment P1. So now it's 2 and 3. Still 2 is smaller, so I add 2 to this list. I increment, this pointer, this goes to 8. Now notice it's 3 and 8 situations are reversed. Clearly 3 is smaller, so I will add 3 to the list and I'll increment P2. So which means my next comparison will be between 4 and 8. Again, 4 is smaller, so I increment P2. I add 4, I increment P2. Now it's 8 and 9. This time round, I increment P1. I add 8 and increment P1, so it's 9 and 12. Clearly 9 is smaller, so I add 9 here. I increment P2. It becomes 12 and 12 less than equal to. So I increment, 12. I add 12 here. I increment P1. So it's 12 and 17. I go and add this 12 here. I increment P2. 13 and 17. I add P2 here. Now this is where it gets interesting. I add, 13 to this list. I increment P2. The moment I do that, notice P2 has become more than the length of the list it was pointing at. The algorithm terminates, and since the last item remains, because of sorted nature, I can just put it in the end. So this item gets added, and the entire list is available. Think through this. Really interesting. See how it's avoiding all kinds of redundant comparisons and just making sure that the list order is maintained. Interestingly, this algorithm works even if the lists are not of equal length, because the key point here is that we are running the algorithm till the pointers on both the lists are pointing within their respective lists. Any items can then be, because the list being sorted, can be accommodated later. Now, very interesting point implication of this is that we may or may not exhaust the shorter list first. It all depends on the values of the list. So let's take two more examples to sort of understand both these points. Basically, let's say we have two lists now. We have a little bit longer compared to B. In this case, I start from somewhere in the middle, let's say 12 and 17. So clearly 12 goes in here. I increment P2, 13, 17. 13 goes in here. I increment P2. Algorithm stops because P2 has become more than the length of B. Now P2 has gotten over. 17 and 18 can be added to this list because by the definition they are sorted, and hence the entire list will end up sorted. So these two are added sort of after, let's say, the algorithm has gotten over. This part of the algorithm, but let's say this incrementing of the pointers has gotten over. Let's take another scenario. So basically in this scenario, the algorithm did stop when the shorter list was exhausted. But let's look at another scenario. Here we have 38 on the last item. So once again, same thing. 12 and 17, I add 12. I increment P2. Now it's 17 and 38. Now in this case, I'm going to increment P1 because clearly 17 is smaller. It becomes 1838. I add 18 to the list. I increment P1. Algorithm stops. Importantly, think about it. Interestingly, this is stopping this time because P1 is becoming more than the length of the list that it's pointing at. P1 is becoming more than the length of A. So in this case, I will not stop when the shorter list is exhausted. In fact, the longer list will get exhausted first. But once that happens, I know that this 38 or whatever follows behind this because of the sorted nature can be added here, right? So the point is, in all cases, the fact that the list is sorted is making it, very efficient. Think about it. The worst case comparisons we do is the length of the longer list, because at that point the algorithm, the movement of pointers has to stop, and the remaining items can be just added. So clearly, this is becoming efficient. We'll write this in code, and that will make it even more clear. I hope you found this interesting. Do look at our website www.ybyte.in. We have lots and lots of materials for you to learn Python, algorithms, programming, and enjoy coding. Take care. Thank you so much. Bye bye.